Okay, so now we will apply the general balance equation to derive a mole balance for a CSTR, or continuously stirred tank reactor. Before we do that, let's see how the CSTR works. So I'm going to click on this link from the University of Michigan Equipment Encyclopedia. That's going to take me to this YouTube video of a CSTR. So you see here we have two inlet flows, one yellow, one blue. They're coming into a tank of pink liquid. The entire tank is this pink liquid, and then we have the entire tank is this pink liquid, and then the pink liquid is exiting here. So going back to the notes, how does the CST operate? So the CSTR is a continuous reactor. So we have some sort of a tank reactor. And in this case, it was liquid. That doesn't look too much like a liquid, so let me redo that. There. And so in this case, we had two inlet flows. So two streams being fed into the liquid. So notice here that the system is this liquid. So when we talk about volume, we're talking about the system volume. In this case, it's this volume. So it's not the tank volume, it's the liquid volume. So as you see, we have two streams coming in, and they are coming into the liquid system. They are dumping into here. And then in this case, we had one stream exiting. So one thing that we noticed in the CSTR video is that this entire liquid was pink. So we had two inflows, one yellow, one blue, and then this entire system here, this entire liquid was pink. And what that's telling us is that this is a well-mixed, the CSTR is well-mixed. So that it's all of the system variables in here are uniform. In the case of the video, we just saw the cartoon, the color was pink consistently throughout. So the assumptions of the CSTR, one is it's well mixed. Another is that it's steady state. The last one is characteristic of the CSTR. So basically, when the contents the contents dump into this liquid here, and then the tank, we have a draw coming out, so an effluent stream or an exit stream. The exit stream is the same concentration, is all the same concentration, temperatures, all the same system variables as the fluid inside the tank. So the CSTR operates the exit conditions. So the concentration temperature of this stream is the same as the concentration temperature of what's in here. So taking these into account, let's write the general balance equation. In fact, let's skip the general balance equation and just write the balance. So we said that this is a steady state reactor, so let's not even worry about the accumulation term. We're just going to call that equal to 0. And we'll write this for species A, but we could write it for any other species. In minus out. And then we have this generation term, net generation of A. But since the CSTR is well mixed, we know that GA is equal to RA times V. So we have 0. Oops. plus RAV. Now this is the general case. So typically when we write a balance, we're trying to solve for something. So if there's two variables here really. One is, well, assuming that the rate is known, we have an expression for the rate. One of those variables is the exit flow rate of A. So what that would tell us is how much A reacted in the reactor by how much is coming out. The other one is the volume. So we're either going to know one or the other. We're going to be given a problem that says we need a specific conversion of A or a specific flow rate of A coming out. What volume do we need? Or we're going to be given a problem that says we know the volume, what flow rate of A or what conversion of A can we achieve? So in this case, let's write the mole balance for V. So we're going to say V is equal to FA net minus FA O over minus RA. And so this is the CSTR mole balance that you'll find, for example, in table S1-1 in Fogler.